In this video, we're going to talk about section 7.2 confidence intervals where sigma is unknown. This is part 2 of our video series for section 7.2, and it picks up on page 4 of your guided notes. Pause the video and make sure you have your guided notes so you can get started with us. First, we're going to talk about the student t-distribution. So this is a distribution that was discovered in 1908 by W.S. Gossett. So he was employed as a statistician by the Guinness Brewing Company, and the company discouraged publication of their research by its employees. So Gossett published his research under a pseudonym, Student. And kind of in his honor, they still call it the student t-distribution. He was the first to recognize the importance of developing statistical methods for obtaining reliable information from samples and populations with unknown sigma or population standard deviations. Gossett used the variable t when he introduced the distribution in 1908, so we still call it the student t-distribution. It might be more fitting to call it Gossett's t-distribution, but literature of mathematical statistics, it's still known as student t-distribution. So it was just invented or created by a guy who worked for Guinness Beer, something that most of us are familiar with. Here are some properties of it. The distribution is symmetric, and the mean of the distribution is 0. The distribution depends on something called degrees of freedom, and the degrees of freedom are given df is equal to n minus 1, where n is your sample size. So if I had a sample size of 10, the degrees of freedom would be 10 minus 1, or 9. If I had a sample size of 25, the degrees of freedom would be 24 in that case. So for this t-distribution, it is bell-shaped, but you'll notice that it has a thicker tail than the standard distribution. What does that mean? It doesn't approach the x-axis as quickly. It hangs above the x-axis a little higher for longer. And as the degrees of freedom increase, the t-distribution approaches a standard normal distribution. So it looks more and more like a standard normal distribution. And the area under the curve is also 1. That allows us to find associated probabilities. Here we have two t-distribution representations. I want to take a look at the one on the right though. You can see in blue we have the standard normal distribution. I would like to draw your attention to the fact that for the standard normal distribution, look, its bell, the top of the bell is up higher, but then down on the right and left legs, the tails are lower. Now a t-distribution with n equals 3 here in orange has the lowest top of the bell, but the highest tails. So see, the tails are higher. Whereas when you increase n to 12, the bell gets higher at the top, but the tail is a little bit lower, still above the normal distribution. Here's a copy of the t-distribution. You also have one in your notes. I'm going to try to show you how to use it. So here we have our degrees of freedom on the right, and that is what's equal to n minus 1. We have our area and one tail listed. Well, that's what we know as alpha divided by 2. The area in 2 tails would simply be our alpha value. So as an example, let's say I have n is equal to 18, and I want to find a 95% confidence interval. Well, first thing I'd do is I'd find my degrees of freedom. Degrees of freedom is n minus 1. So 18 minus 1 equals 17. So I'm going to go ahead on my chart and find my degrees of freedom is 17. I'm going to mark off that whole row across. Next, you have 95% confidence interval. Well, that means we have alpha equals 1 minus 0.95 or 0.05. So I'm going to go ahead here and find the area in the 2 tails, or alpha is 0.05, and I'm going to mark off that column. Where my row and my column meet is at 2.110. So our critical value, t, is equal to 2.110 in this problem. Because we have the t-distribution, we can find confidence intervals for when sigma is unknown. Just like when sigma is known, the confidence interval format is you take x bar minus e, and then you take x bar plus e to get your limits for your confidence interval. Now, e represents error, and x bar is our sample mean. But the formula for e is your critical value times the standard deviation of the sample divided by the square root of n. You'll see here we have some calculator instructions, and I do recommend the use of them, but for confidence intervals, I'm going to show you how to do this by hand, and then I'm going to show you two different ways to do an example in the calculator. So we're going to do the example you see here, and we're going to do it 3 times using 3 different methods. Example states, suppose an archaeologist discovers 7 fossil skeletons from a previously unknown species of miniature horse. Reconstructions of skeletons of these 7 miniature horses show the shoulder heights in centimeters to be 45.3, 47.1, 44.2, 46.8, 46.5, 45.5, and 47.6. For these sample data, the mean is 46.14 and the sample standard deviation is 1.19. Let mu be the mean shoulder height for the entire species of miniature horse and assume that the population of the shoulder heights is approximately normal. Find a 99% confidence interval for mu. I've written down the information given in the problem on the left here, and as you can see, we were not given a population standard deviation, only a sample standard deviation. That means that sigma is unknown. And I usually write that right next to the problem. It's a good habit, so that way I don't accidentally use the wrong formula or process. So what we need to do is find the error. E equals t times s over the square root of n. So let's go to our degrees of freedom table, our t distribution, and find t. So since n is 7, we know our degrees of freedom is n minus 1. So degrees of freedom is 6 in this problem. So I'm going to highlight that row. For a 99% confidence interval, we would have our alpha is 0.01 because 1 minus 0.99 is 0.01. So we can see that these meet at 3.707. So that is our value of t. So we fill in our formula with the information we know, and when we calculate 3.707 times 1.19 over the square root of n, we get 1.667, and that represents the error in this problem. To get our confidence interval, we have to find the boundaries for it. So the lower boundary is 46.14 minus 1.667, our sample mean minus our error, and then our upper bound is 46.14 plus 1.667, and we'll get our final confidence interval as 44.473 to 47.807. So that's the 99% confidence interval of the mean shoulder height for miniature horses. We're going to go back and use our calculators to do this problem, and we'll do it 2 different ways. First, we're going to go to Stat, over to Tests, and we're going to find where it says T interval, which is option 8. So you can select 8 or scroll down and press Enter. I'm going to go ahead and press Stats first, the first time I go through it, because we're given all of the stats for the problem. We have 46.14 for the mean. We have the sample standard deviation is 1.19, and then n was 7. Remember, we have a 99% confidence level, so 0.99, and then go ahead and calculate, and you'll see we come up with the same answer, 44.472 to 47.808. We're off by 1/1000th on the upper interval, but that's due to rounding in when we did it by hand. Now we're going to try the problem again by plugging in our data. So we're going to go to Stat to edit, and you'll see here that I've plugged in all of our data for our 7 values that were given in the problem. Go ahead, pause the video, and make sure you have the data plugged in as well. So now, once you have your data plugged in, you'll press Stat again and go over to Tests, and you're going to go down to T interval, which is number 8, And this time, highlight the word data and press enter. I put my data in list 1, so I want to make sure I have list 1 covered. Remember, you press second and then the number for whatever list you put your data in, -1. Frequency, just leave as is because we didn't use the frequency. Make sure you have a 99% confidence interval. Go ahead and press enter, and you should come up with the same confidence interval once again for a third time. Now, what do you show for work if you did this problem using your calculator? Well, you'll write on your paper t-interval. You should list the important information that I'm highlighting right here, and you should list your final answer. Now, if you have a t-interval problem and you also have to find the error, but you used your calculator, remember, we can always use the idea of the error can be found by taking the upper limit minus the lower limit of your confidence interval and dividing by 2. Make sure you take a look at the summary on page 7 of your guided notes document, and then go ahead and try the practice problems on pages 8 and 9. The answers and work will be posted to Blackboard for you to check with. Keep up the good work. You're doing great.